We had a lot to unpack in today. We talked about exact differential equations, and we also talked about substitution. And these are both important ideas. And so we didn't have a lot of time to go through and solve as many as we would have liked. So let's take some time and do that. So we're going to go through and do a lot of problems. In some sense, we're going to finish a lot of problems because we start a lot of problems by saying, here's the substitution, and we get to a point, and we could finish it up if we had time. Well, now we have time. So you'll say, it's a lot of deja vu. Now, don't feel like you have to watch everything. Watch what you need. And spoiler, if you look on the bottom, you'll see you can jump to different content very quickly. So jump to what you need, find it, and learn. Have fun. Get great at it, because we know you can do it. Let's look at a problem involving an exact differential equation. So this one is going to be a little bit different in that we're going to actually have a point specified. We never actually did that in class, so let's do it now. But the ideas are pretty similar. Now, we suspect that this is an exact differential equation, well, because I said it, but also because it's very messy. And you might say, well, how do we distinguish the right kind of mess? Like, there's a mess like, is it a kind of mess that's good for substitution, or does it really have to be exact? And that's a great philosophical question. Usually, if you're trying to think substitution, you'll look for like a function inside a function. But when you see y involved in multiple different ways, like inside the exponential, down in the denominator, when you see so many different behaviors of y, no one substitution is going to work. So we shouldn't be trying substitution on something like this. Well, we're not going to. It's exact. Now, the first thing we'll do is rewrite it. We'll think of this as a dx separated from the dy and multiply through. And so we'll have x e to the xy plus 2xy plus 1 over y dy plus y e to the xy plus y squared plus 10 dx equals 0. All right, good. Now, in this form, we say, hey, we see what we need to do. We need to integrate our two parts. Now notice the dy came before the dx this time. Sometimes it comes after. So the way you remember is you say, look, whatever the dy is attached to, integrate that part with respect to y. Whatever the dx is attached to, integrate that part with respect to x. That's it. We don't have to be like, oh, wait, do we do this? No. Just do what feels obvious. Well, that's a dangerous thing to say. But we'll integrate the first term, x e to the xy plus 2xy plus 1 over y dy. Now here, since we're integrating with respect to y, x is a constant, so there's no integration by parts. And here, when the x stays there, e to the xy, the integral of that would be e to the xy, divide out the constant, which is x. So what you'd have is x over x, which would give you e to the xy. The next term, well, x is a constant. We're integrating with respect to y, x, y squared. And 1 over y, integral that, log y. And then, of course, some constant function of x. All right, well, good. That part's done. Now we integrate the other part. So we'll have the integral of the second part, y e to the xy plus y squared plus 10 dx. Now, of course, we're switching hats. Now, x is our variable, so don't forget. Same idea with the first integral. Since x is our variable, y is a constant. So when you integrate the first term, y stays alone. Nothing changes. The e to the xy, you divide out by the constant, which is the y, and you end up with e to the xy. Integral of y squared, well, that's just an integral of a constant, so it's the constant times x. Right, that's xy squared. Integral of 10 is 10x. And then, of course, add some unknown function of y. Okay, so at this stage, we go into our check. We say, all right, look for the terms, and the terms are the part separated by plus signs. So there's 1, 2, 3 terms plus your constant function, 1, 2, 3 terms plus your constant function. So we compare the terms that involve both x and y. We can't separate. And we see, yes, lo and behold, they match, which means it is exact. And we can start building our function by putting that part down, e to the xy plus xy squared. And now we go through and grab our pieces. So here we can grab our term just involving x plus 10x. And then from our other term, we can grab our term just involving y plus natural log of y equals a constant. I suppose I should keep working my way up through the alphabet. So equals e. Now, because we have an initial point, that says we're not done yet. What we need to do is it passes through the point 0, 1. So we should be thinking of this as x comma y. So in other words, x equals 0, y equals 1 should satisfy this equation. So we plug those in. E to the 0 times 1 plus 0 times 1 squared plus 10 times 0 plus log of 1. Well, okay, a lot of stuff cancels because, 0, 0, 0, and get 0 upstairs. Of course, that's e to the 0, which is 1. So that's how you find e. Plug the point in, and life is good. So our final answer, e to the xy plus xy squared plus 10x plus log of y is equal to equal to 1. All right. We'll rewrite that. Why not? I was just so excited from copying. A lot of differential equations becomes copying. But of course, a lot of mistakes are, whoops, you didn't copy it right. Well, there we go. Equals 1. Life is good. Let's do another problem. Solve the differential equation dy dx equals 4e to the 4x minus 2xy squared. Divide by cosine y plus 2x squared y. And again, we look and say, hopeless, hopeless. I mean, look at how the y's are there and the x's are there. Some things are in a function, some things are out of function. It's just, there's nothing. There's no simple technique. There's no substitution. Which means when it's hopeless, we're like, go for exact. And this one is probably going to be the one that really most highlights that you may have to do a little bit of rewriting. But that's okay. We're okay with that. I mean, rewriting, that's the bread and butter of doing a lot of math. Because oftentimes, the way you solve a problem is you rewrite it to something simpler, and you rewrite that to something simpler, and And all of a sudden, whoa, that's so simple, that's the answer. Who knew? That's how math works. Well, we all kind of know after a while. So how do we make this look like the normal thing? Well, if you have this, what we would do is what we call cross multiply. So we're just, multiplying the terms across. And so what we would have is cosine y plus 2x squared y dy is equal to 4e to the 4x minus 2x y squared dx. Now you might say, good, ready to integrate. No, not yet. You have to get into the right form, which means everything has to be on the same side. So you gotta move stuff over. So we're gonna move that across. So we're gonna subtract it. Now I could put minus, but what I'm gonna do is I'm gonna just add the negatives of everything. So it's cosine y plus 2x squared y dy plus minus 4e to the 4x plus 2xy squared dx equals 0. And now we're ready. We think that this should work. Well, if it doesn't, hopeless, right? Well, but we have faith. Integrate the first term. So cosine y plus 2x squared y. We're integrating that with respect to y. So y is the variable, the integral of cosine. Ooh, the tricky one. It's positive sign. Yeah, right. Good job. Good job. You got this. You got this. Integral of 2x squared y. Now we're integrating with respect to y. So the x squared is the constant. Integral of 2y would be y squared. And then, of course, something which depends just on x. Now, integrate the second term because, well, we should. Integral, we have minus 4 e to the 4x plus 2xy squared dx. Now in the first term, well, integral of e to the 4x would be e to the 4x divided by that constant, so the 4's cancel. So minus e to the 4x. Here, x is our variable, so it would become x squared y squared, and then some unknown function of y. And now we go and check. That's our second step. So after we integrate, we say, well, look, group the terms that depend on just x and y. And check that they're equal, and they are. Woohoo! Which means we have a solution. It is exact. So we write stuff down. The parts that match, we write that down. The parts that just depend on x, all right, we write that down. And then we say, all right, the parts that just depend on y, all right, we write that down. And finally we say, okay, and this is equal to some unknown constant, and there's there's no other information, there's no initial conditions, and therefore we're done. That's it. That's it. So the hard part about this one is getting started, knowing that you need to do exact. Again, if it's hopeless, then you have hope, right? It's one of those fun ironies. In some sense, exact ones are pretty quick, if you know what it is exact. But be ready. A lot of math comes from rewriting and simplifying. Not just here, over and over and over. If you can master the art of rewriting, you're going to do great. So we joined this problem currently in progress. Now this was y prime equals 4x plus y plus 3 quantity squared. And there's often a question, how do I know what to substitute? And I don't know if there's a great answer for that, but generally speaking, you say, okay, how is your part that you're taking derivative of? In this case, it's the y. So you want to make sure which is the function that you're taking derivatives of. So you have that identified. You say, okay, so y. Y is the thing involved in derivative. How is that, the function on the inside of something? Like, what's the right function to identify? Because when you're looking for a substitution, that's often the way you go. Now here, it's kind of a little clear because you say, oh, I have something squared, so the something is the thing on the inside. So you make that substitution is equals 4x plus y plus 3. And remember, when we substitute, so we're really substituting for the y. It just happens to grab a couple of other stuff, of other terms, I should say, along the way. But you also got to account for that y prime. So we take derivatives, z prime equals 4 plus y, and this became z prime equals z squared plus 4. So that's where we were at. Now, the continuation. Well, this is actually going to be a separable differential equation. So this is dz over dx is equal to z squared plus 4. And then we would move the z squared plus 4, move the dx. We would get that dz over z squared plus 4 is equal to dx. All right, good. So that's the separation part. Now the fun part, or the not so fun part, depending upon how you feel about things, is the integration. Well, one of these sides at least is pretty straightforward. That's right. This side, which, oh wait, no, that's not the side you were thinking about. Yeah, the right-hand side, there's no big surprises. So we get x plus some constant c. Okay, so what about the left-hand side? You might be thinking arctangent. Good for you. That's actually what it is. Now, it's a little bit more subtle because, our formula sheet, or the ones that we tend to memorize, is z squared plus 1. Now, I don't encourage you to memorize lots of variations, and so I'm not going to say, aha, well, this is one that you should all know, right? No, I don't want that. I would say z squared plus 4 downstairs, probably we wouldn't ask you to do that live. Z squared plus 1, oh yeah, you're going to see that. You're going to have people who are like, I love arctangent, because, there's people like that out there. So how could you do this? Well, one way you can do this is you say, well, I'm going to pull out a fourth. And that seems like a strange thing to do. So what we're really doing is pulling out a 1/4 in the denominator. And so this is plus 1. Now, this would be z squared over 4, or if you like, z over 2 squared. All right. And now you're like, oh, I see where you're going with this. You're saying make a substitution. I am saying that. U equals z over 2, and so du is 1/2 dz. Well, we have a fourth there, so we can think of this fourth as a half times a half. So this would become 1/2 integral du over u squared plus 1. Well, okay, great. That's easy, 1/2 arctangent u. Now, I don't need a constant because there's already a constant over there. And, well, we update. That's 1/2 arctangent of u is z over 2. And, great. Now, are we done? No, but we're close. We're close. Now, we're not done for the same reason we're not done when we do substitution in Calc 1. Everything has to go back in terms of the original. Now, original was 4x plus y plus 3, so we've got to replace z. Now, you might say, could we clean it up a little bit first? And we say, yeah, sure, why not? So we like clean answers. And so what we'll do here is we'll take our expression and let's multiply both sides by 2. Just get rid of that half. Now, that would give us that arctangent of z over 2 is equal to 2x. What comes next? Plus c. Now, you're probably like, c, shouldn't it be 2c? This is one of those, remember, constants like to absorb constants. So 2 times c is still a constant. So constants are sponges. Get rid of the arctangent by doing tangent both sides. Z over 2 equals tangent of 2x plus c. Or we could say z is equal to 2 times tangent of 2x plus c. Great. And finally, to finish it up, we replace z. You're not done until you get back in terms of your original. And so we have 4x plus y plus 3 equals 2 tangent of 2x plus c. And that is our answer. Now we're done. Beautiful. Beautiful. We're joining this problem currently in progress. So the problem said, solve, you have x minus y times y prime equals x plus y. And we said, hey, look, all these terms, they're kind of polynomial with the same degree. So that's homogeneous, same degree. And what you do is you say, look, I'm going to make everything look like a y over x. So here you just divide out by x, or if you like, multiply everything by 1 over x. And the substitution is to say, oh, well, notice how every time I see a y, it's involved with y over x, and therefore we substitute z equals y over x. That's a thing you look for. How is your y involved? If it's consistently involved in one way, that's the substitution to make. So you make the substitution z equals y over x. If you solve for y, you get y equals x times z, and you can find y prime equals z plus xz prime. And so this becomes, after a little bit of algebra, xz prime equals 1 plus z over 1 minus z minus z. So there's a little bit of stuff that was done before, but now we join our problem currently in So, how do we keep going? Well, here we have some terms being combined. So what we'll do is we'll combine them. So we want to get a common denominator. So we'll think about timesing the second term by 1 minus z over 1 minus z. So if we did that, we'd have 1 plus z minus z, so z and minus z squared. So I multiplied the z through over 1 minus z. Okay, well, what's that? Well, the z's cancel, and we end up with 1 plus z squared over 1 minus z. Okay, good. And remember, that was over here. So that's x z prime, which is x dz dx. Now we're ready to do our rewriting. And so this becomes, when we separate, we'll have, this will flip when we take it across. So we'll have 1 minus z over 1 plus z squared times dz equals 1 over x dx. All right, well, integrate. We've done our separation. Now comes the integration. And, well, what do we get? Now, on the left-hand side, this is 1 over 1 plus z squared minus z over 1 plus z squared. So we're using the fact that upstairs we have, a minus. This minus up here, this is what we would call a good minus. So addition or subtraction upstairs, we love that because that lets us pull terms apart. Addition or subtraction downstairs, we're not so thrilled about. It requires a more delicate touch because you can't just pull it apart. You got to work a little bit, but that's okay. That's why we learn stuff, to help us. Now, just in anticipation, because we've seen integrals like this before, we're going to put a 2 and a 1/2. So notice 2 and a half, they cancel out. And why did we anticipate? Well, if you let u equal 1 plus z squared, du is 2z dz. So it's like a 1 over u du. This is an arctangent, which we know. And of course, the integral of 1 over x, well, hey, we know that too. And so we get the following. We get arctangent, we'll move up here, arctangent of z minus 1/2 natural log 1 plus z squared is equal to natural log of x plus c. Now, are we done? No, right? Because we're not done until we get back in terms of what we start with. So we got to replace whatever we substituted. And so we'll go through here, and everywhere where we see a z, we're going to put a y over x. Even if it doesn't look great, we're still going to do it because that's what z is. We have no choice. So we get that arctangent of z, y over x, minus 1/2 natural log of 1 plus y over x squared is equal to natural log of x plus c. Now, could you leave your answer like this? Yes. Would you get the credit? Yes. Am I being mysterious because something cool is about to happen? Yes. So this is fine if you left it here. But you know what? We're just going to have a little bit more fun. A little bit more algebra. Who doesn't need more algebra in their day? I can't think of anybody who wouldn't benefit from a little bit more algebra. Now, what's our little more algebra? Well, we're going to look at this term, this natural log of 1 plus y over x squared, for a moment. Now, this would be y squared over x squared, and now get common denominator. So you'd end up with a natural log of x squared plus y squared over x squared, if you simplify just that part. But by properties of logs, this would be natural log of the top, x squared plus y squared, subtract natural log of the bottom. But wait, notice this is natural log of x squared plus y squared minus 2 natural log x. Now, why do I say, but wait, notice, you have a minus a half in front. So you're going to have minus a half log x squared plus y squared minus a half times minus 2 log x. Well, minus a half times minus 2 also goes by the name of 1. Which means that if you take this minus a half and this minus 2 log x, it's exactly equal to that log x. In other words, they cancel, which means that we can write our answer in the following way, namely this part, our arctangent of y over x, did not plan well on that part, okay, minus 1/2 log x squared plus y squared is equal to c. There you go. That's another way to write the answer. See, somehow you might say, it's amazing that we had a log x show up, but it also disappeared. You know, math finds a way. It finds a way to sort of correct itself if it ever needs to. Wow, isn't that cool? I think it's cool. I think it's cool. So a problem from scratch. Solve 2xy dy dx equals 4x squared plus 3y squared. Now, when we look at this, we would say, okay, well, what does it look like? We say all the pieces are polynomial, and we say, oh, well, what's their degrees? Well, it'd be 2, 2, 2. Now, 2 because there's one x and one y, so there's a total of 2 terms. Say, oh, everything has the same power, which means everything's homogeneous. So, say, hey, idea. Take our equation, and we're going to multiply by 1 over x to whatever that power was. In our case, the power was 2. And making that, we get that this will become 2 y over x dy dx, or y prime, is equal to 4 plus 3 y over x squared. All right. My spacing is not very good on the right up here, but you see what I mean. And now we say, look, y over x there's our substitution. Well, yeah, that's the point of homogeneous. So we're doing c equals y over x. That'll take care of that term and that term. Now this is not a y over x. dy over dx is something different, but we do have to account for it. Okay, or we could say that, look, y is equal to z times x. And so y prime, which is the dy dx, is equal to z plus z prime times x, which is, we did a product rule there. The first times the root of the second plus the root of the first times the second. So this becomes, once we've done our substitution, we have a 2, then the y over x becomes a z. Our y prime becomes a z plus z prime x. And this is going to be equal to 4 plus 3z squared. All right. Well, we're almost there. We multiply through. We have 2z squared plus 2z z prime x equals 4 plus 3z squared. Well, we subtract across. We have 2z z prime x is equal to 4 plus z squared. And we say, aha, ha ha, ha 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 ha. Well, whatever noises you make when you say, this is separable, because it is. It is separable. Now, this is if we rewrite this side, this is 2z dz dx times x. And so the x and dx come across, the 4 plus z squared comes across. So we have 2z over 4 plus z squared dz is equal to 1 over x dx. And now we integrate both sides. So I say, all right, what happens? Well, it turns out these are both lovely integrals. 1 over x, that's a known one. Get log x plus c. Now here, u equals 4 plus z squared. du would be 2z dz. So it's, the derivative on the top, function on the bottom, which means it's a log of what's downstairs. So we get log of 4 plus z squared. Now here, let's take both sides. Since everything involved is log, we exponentiate both sides. And this will become, after we simplify, z squared plus 4 will be equal to, e to the log x will be x, e to the c will be a constant, but they're no longer being added, they're being multiplied. So since e to the c is a constant, we'll write constant x. Now, we're not done because we got to replace z. So this would become y over x quantity squared plus 4 equals some constant x. And this is a great way to leave your answer, but if you're like me, you're like, let's get rid of fractions. What you can do is multiply through by x squared. Now, you might say, to compensate for that? No, that's kind of coincidence, but same philosophy, right? Here we wanted to introduce an x squared downstairs. Here we want to get rid of an x squared downstairs. And so multiplying through by x squared just to make things look nice, because don't we want things to look nice? I think so. We end up with y squared plus 4x squared is equal to some constant x cubed. That's it. Wow. So we're going to join this problem currently in progress. So the problem was xy prime plus 6y equals 3xy to the 4/3. And this is one where if you were to cover up that last piece, it looks linear. So the problem is that you have this x y to the 4/3. Now, this is called Bernoulli. And you might think, well, okay, what was Bernoulli's idea? Well, Bernoulli's idea is actually not a very sophisticated one. Bernoulli was probably thinking, I'll make a substitution that looks like z equals y to some power. That was Bernoulli's idea. And you're like, that's Bernoulli's idea? That's it? Like, yeah, that's it. It's not very sophisticated at all when you say it out loud. The hard part, of course, is just saying, well, which is the right power? So how do you do it? Well, what you do is you divide everything by this extra term, y to the 4/3. So you have x, y to the minus 4/3, y prime, 6y to the minus 1/3 equals 3x. Now you might say, well, wait, is it the y to the minus 4/3 or the y to the 1/3? And the answer is, it's the y to the 1/3. The way I think about it is, the y prime is going to show up after I take the derivative. So this part is essentially capturing the derivative of my substitution. So that would be my substitution. So that's where we get our substitution from. So we set z equal y to the minus 1/3. You work it out. That says that minus 3z prime equals y to the minus 4/3 y prime, which becomes, after you clean it up, z prime minus 2 over x z equals minus 1. Okay, so that's where we're turning our problem. So we continue now. Well, the next thing to say is, well, this is a linear first order. So Bernoulli, the goal is to actually turn things into linear first order. And we say, all right, great, which is why we wanted to make this a 1 in the front. So when we're solving linear first order, we take our coefficient here, and we integrate that coefficient. That's minus 2 over x. And that would be minus 2 natural log of x which is natural log of x to the minus 2, or if you like, 1 over x squared. Remember, we don't need to worry about constants when we're looking for integrating factors. So rho of x is e to this function, and e and log undo each other, so 1 over x squared. All right, so now you go back to this part right here. The part where you were looking for your integrating factor, we're multiplying everything by 1 over x squared. Now, doing that, what happens? Well, what we end up with is 1 over x squared z prime minus 2 over x cubed z is equal to minus 1 over x squared. Now I'm going to write this other side as minus x to minus 2. This side is really, by design, the derivative with respect to x of 1 over x squared times z. And if you're in doubt of what you did, just quickly do a product rule and check. Then derivative of 1 over x squared is indeed minus 2 over x cubed. Okay, so from here, we now say we're ready to integrate, because the part that's hard, the stuff that involves the z, is inside a derivative, and, well, derivatives are easy to integrate. And what we end up with is 1 over x squared times z is equal to, well, okay, here you would add 1 to the exponent, so it would be minus 1, divide by minus 1, so it's x to minus 1, which is 1 over x, and of course plus c. So now multiply through, and we end up with z is equal to x plus some constant times x squared. All right, good. Well, progress, great progress actually. So now what do we do? What do we do here? Well, our next step is to replace the z, because we're not done till everything's in terms of your original variable. So we say, we see what z should be. It's over here. Z equals y to the minus 1/3. So we say, okay, this equals y to the minus 1/3. Now, if I wanted to solve for y, I could raise both sides to the minus 3. So if you take something raised to the minus 1/3 power, raised to the minus 3 power, see the powers multiply, you get something to the 1. And so we can say that y is equal to something that looks like x plus some constant x squared, all raised to the power minus 3. And we're done. That's it. Woohoo! We did it! So a problem started from scratch. So we get to do the whole thing. Solve the differential equation, x squared y prime plus 2xy equals 5y to the 4th. Now, you might say, well, what's our technique? And of course, if you're watching this sequentially, you'll be like, hey, I know what this is. This will be Bernoulli. And they might say, how do you know that? Well, because if I covered up that y to the 4th on the end, it looks perfectly like a linear. So here, because there's this extra power of y, Bernoulli says, I can fix that. I know how to get rid of it. Now, be a little bit careful here. So for example, this had been 5y to the 4th plus 6, not Bernoulli. Whatever's over here, the power of y has to multiply the whole side. Can't just be a piece of the side. So if it's not the whole side being multiplied by y to the power, forget it. Stop. But we're okay. So we're not going to stop. We're going to go all the way. Which means what? Well, okay. First off, rewriting. Because, well, that's what a lot of math comes down to. We say that a lot, but it's true. So in our case, we're going to divide by that y to the 4th, because that's going to help us understand what's going on. So x squared, 1 over y to the 4th, y prime, plus 2x, 1 over y cubed, equals 5. Don't worry about like, oh, am I dividing by 0 or not? No, don't worry about that. Those details we iron out at the end. We never worry about that in the process. So, for the substitution, when we're thinking Bernoulli, it's the part that's not attached to the y prime. So 1 over y to the third power. Remember, Bernoulli just says, hey, I'm just looking for a power of y. What's the right power of y for me to substitute? So once you found that, life is good. Life is wonderful. So we have our substitution. Z is 1 over y cubed. Let's go ahead and write that as y to the minus 3. If we take z prime, that would be minus 3 y to the minus 4. Well, that's basically what we have here, except for that minus 3. Okay, so that's minus 1 over 3 z prime is, oh, I forgot my y prime there. Thanks for catching that. So minus 1/3 z prime is equal to 1 over y to the 4th y prime. Okay, so there's our substitution. Okay, let's go ahead and we'll carry that substitution through, and let's see what we get. So we're going to get x squared times minus 1/3 z prime. So I'm going to write that as minus 1/3 x squared z prime plus 2x times z. All right, cool. Equals, on the other hand, well, nothing's happening, equals 5. So we have our differential equation. Notice all the y's are gone. That's what happens with substitution. All of our old variable has become the new variable. If you still have y's left, you haven't finished substituting. That, or a poor choice for substitution has been made. Well, one of those two is probably true. All right. Well, now let's see, what can we do here? Well, here we say, okay, we want to get the z prime to just be a 1. That's how we do it with linear first order. So we're going to multiply through by minus 3, divide by x squared. So if we do that, we'll get z prime. Okay, so we're multiplying by minus 3, so it becomes minus 6. Divide by x squared would be 1 over x, z, and over here be minus 15 over x squared. All right. Now this is just temporary. We're going to update in a moment. So don't worry if the terms look unpleasant now. They'll change to something. Maybe something still unpleasant, but maybe not. We got to figure it out. So we grab the term. We're going to integrate that. Don't forget the minus comes along with that. And we see, this is very predictable. We see things like this all the time. So this is the natural log of x to the power negative 6. So our integrating factor will be e to that, which is x to the minus 6, or if you like, 1 over x to the 6th power. So that's, well, it is what it is. All right, so we continue. Take that, multiply everything by 1 over x to the 6th. And what do we have? Well, we end up with the following. We have 1 over x to the 6th, z prime, minus 6 over x to the 7 times z is equal to minus 15, and then it'll be x squared downstairs, x to the 6 downstairs, so x to the minus 8. All right. Well, by design, this left-hand side is the derivative of 1 over x to the 6 times z, and the other side, minus 15 x to the minus 8. But the point here is these are not bad. These are things that we can integrate. We can integrate both of these things. So we integrate, and we integrate. So we have, moving on up, 1 over x to the 6 times z. That's that side. Equals, okay, so here we'd add 1, so that would make it x to the minus 7. We divide by minus 7. So the minuses cancel out. 15 sevenths x to the negative 7 and plus c, multiply through by x to the 6. So this is really 1 over x to the 7, multiply through by x to the 6. We would end up with saying that z is equal to 15/7 times 1 over x. So I'll put 15 over 7x plus some constant c times x to the power 6. All right, now that's z. It's not y. So we have to come along. So, well, what is y? Well, z is y to the minus 3. So finally, if we want to solve for y, well, take both sides and raise it to the minus 1/3 power. Because, minus 3 to the minus 1/3, they'll undo each other. And so we end up with finally getting our answer. Y is equal to 15 over 7x plus some constant x to the 6, all raised to the negative 1/3 power. Just like we thought. No, come on. It wasn't just like what we thought. I mean, who would guess this? Who would guess this? Well, no one. That's why we have to do the process. But we did it, and we learned. Woohoo! Good for us. Now we're kind of reaching the end of our simple substitutions. We're going to do a few more after this. There's a punchline, which is to say, look, there's lots and lots of substitutions. And if you just say, oh, I'm going to memorize the 4 different types, I don't know if 4 is the right number, but you got your homogeneous and you got your Bernoulli, and you have look for stuff on the inside. Actually, this look for stuff on the inside is really common. But if you say, look, those are the only things I'll look for, you might miss things. And so just say, okay, what's the goal? The goal is look for good substitutions. Now, what makes a good substitution? Well, you want to say, okay, the part that involves a derivative, can I think of it as the derivative of some function that's showing up someplace else? Especially this will be true if you see y inside of an expression. And so you look for things, and if you look and try things, you'll see, aha, some things will work well. Well, some things maybe not so well. But, we always try. We always try. So let's do a couple of examples here. So some of these probably could be solved in other methods, and some of them maybe wouldn't be so clear. All right, so I'm going to grab some paper here. And so let's start with this first one. Okay, y prime plus x equals the square root x squared plus y squared. Okay, so there's our differential equation. Now, if we were looking at this, putting on our let's look for stuff on the inside hat, what would we see? Well, we say, hey, there's a square root here, and this is inside the square root. Let's try that. You might say, well, should we just try the y squared? No, we should be like, try everything, go big, because, hey, that might work. Okay, so we'll go big. Let's let z equal x squared plus y squared, and so then z prime. And we're really thinking of z as being a function of x. Y is a function of x, and so z is a function of x. So we're taking the derivative with respect to x. We'd have 2x plus 2y, y prime. And we're, whoa, that's almost that side. Yeah, that's the point. That there's a substitution where z prime matches up pretty nicely. Okay, so we could then say, like a half z prime equals, we'll write as y prime plus x. So, making our substitution, we'd have that the left-hand side would be 1/2 z prime. The right-hand side would be square root of z, which we can write as z to the 1/2. This is wonderful. This is separable. So we say, all right, let's separate. So we have z to the minus a half dz, because come over as a minus a half because you have to divide by z to the 1/2, equals to dx. And now we integrate. And so we integrate both sides. And okay, so you add minus a half plus 1, so that would become a half, divide by that, and so that would be 2 square root of z, or if you like z to the 1/2, equals 2x, and then plus some constant c. Well, the 2's cancel. You might say, well, what about the c? It just absorbs that dividing by 2, and so we end up with the square root of x squared plus y squared equals x plus c. Yeah, we could square both sides if we wanted to, but you know what? That's an answer. And so there we go. So it's like, hey, we looked for something on the inside, and we tried it, and it worked. Now, if it didn't work, we would try something else. And oftentimes, a failure, that gives us a hint about how to change our next guess. Okay, so, great. We can do that one. And life is good. All right, let's try another one. I have more paper. It's a wonderful resource. It grows on trees. Well, it is true that it grows on trees. And it is wonderful. Writing stuff down, it's so good for helping us understand. All right. Now, what if we saw this one? Y squared y prime plus 2xy cubed equals 6x. Now, do you actually see what it is? It's really a Bernoulli. It really is, honest to God. I wouldn't lie to you. It's just written in a different way. So we could first write it as Bernoulli, and then we could rewrite it or something, along those lines. Or we can say, well, I see the y squared y prime, I see the y cubed, and in the back of our head we're like, the derivative of y cubed is like 3y squared y prime. It looks just like that. So if we said, oh, that was our substitution, life is good, we're off to the races. You see, we don't have to go through the Bernoulli if we can see our substitution a little earlier. Why not just do it? So let's just do it. All right. So here's our idea. I'm copying it down again. Y squared y prime plus 2x y cubed equals 6x. So we're going to make our substitution. Z is y cubed. dz is 3y squared y prime. And move that 3 across. So this will update to say the following. Namely, we have, why did I write dz? Z prime. I had integration substitution stuck in my head. That happens. Sometimes when you get a lot of math, it's hard to fit it all in. And so what you do is you try to learn patterns. That's actually when you're really doing well in math. Say, look, I'm not going to memorize lots of formulas. I'm going to memorize patterns to formulas. It's somehow I'm becoming meta, It's easier to do. All right. Sorry. Distractions. Let's get back to where we were. So the y squared y prime is our 1/3 z prime. 2xy cubed will be our 2xz. And our 6x will be our 6x, because we're replacing the y's. Our real goal is not to replace the x's right now. We're replacing the y's because that's the y prime. And I say, this is great. This is wonderful. And we say, all right, well, at this stage, we'll multiply through here. And we'll multiply through by 3. And so let's see what we get. We get 6, z prime plus 6xz is equal to 18x. And, well, this side by design. Oh, wait, no. I am so getting ahead of myself. We haven't done any design yet because something really like fun is about to happen. Oh, man. I'll tell you, sometimes you should just take a break, enjoy it. All right, we're going to integrate that. Integral 6x, well, that's 3x squared. And so we take e, and so this is our rho of x. And notice our rho of x is not going to look that simple. In fact, it's going to look really like, But we will not be afraid because we know the process. The process is going to work. So when you multiply this through, we get e to the 3x squared z prime plus 6x e to the 3x squared times z equals 18x e to the 3x squared. Now, let's give ourselves some space. Okay, so this left-hand side is a derivative because that's how these work. E to 3x squared times z, and this right-hand side is what it is. Now you might be like, e to the x squared, how are we going to integrate that? And then you're like, oh, I see what they did there. Yeah, that's right. They set us up to succeed because, that's what mathematicians do. They like you to succeed. That's great. So we have e to the 3x squared times z is going to be equal to, now here's how it's going to work. Over here, we're going to let u equal 3x squared, so that du would be 6x dx. Notice we have an 18x dx, so that would leave us with 3 e to the u. So that leaves us the integral as being 3e to the u, and u is 3x squared. And then, of course, plus c. So we get z is equal, divide through the e to the 3x squared, and then we have divide by e to the 3x squared would leave us with 3 plus some constant e to the minus 3x squared. Now, remember, this is not y, this is z. So, to finish up, we say z is y cubed, and therefore, taking the cube root of both sides, y is equal to the cubed root of 3 plus some constant e to the minus 3x squared. Wow. Wow. That's amazing. Amazing. Cool. Well, life is good. Life is wonderful. But there's more things for us to try. Okay, so let's go back to our list. So we just finished this one. Okay. Well, let's see. What can we do for our next one? All right. Come here. Give us a piece of paper. So we have y squared times xy prime plus y times the square root of 1 plus x to the fourth is equal to x. And you might look at this and say like, ugh, I don't know. What can I see? Well, I'll tell you, there's actually something interesting going on here. Now, you could do a couple things. This is a Bernoulli, and that probably would work. But I want to try something here because my eye is drawn to something. And I don't know if maybe you and I see the same things. I hope we do. I mean, we're both looking at the same place. And so one of the things I'm looking at is when I think about this here. I see a y squared xy prime plus y. Here's a square root of 1 plus x to the fourth equals x. And this truly would work as a Bernoulli type problem. You could do it that way. You'd have to fiddle with it. But here's what I want you to notice. This part right here, this xy prime plus y. Do you see that? And in particular, have you seen anything like it? Or is there another way to think about what that term is doing? If you think about this part right here is a derivative of x times y. And so an idea pops in. Our idea is, well, since that's a derivative, whatever we're taking the derivative of, let's call that our substitution. So let's make our substitution z is equal to x times y. Now, you might say, okay, well, that would mean that this part right here becomes the derivative of z. This becomes z prime. But we also have to make sure we replace that y. So how can we do that? Well, there's a couple things you can do. You can multiply everything by x squared, and then you have an x squared y squared. Or you could say, look, y is equal to z over x. Eventually, whichever way you pick, you'll get there in the end. Okay, so we now have, if we make this z over x squared, that's the y squared, times z prime, times the square root 1 plus x to the fourth is equal to x. Now, at this point, we say, hey, we've done a good substitution in the sense we've been able to replace all our old variables. We don't know if it's a good substitution in the sense, hey, we can integrate this now. That's to be determined. Ultimately, the measure of a substitution is how easy is it to actually carry out and solve. So, well, let's see what happens. We would have, this would become z squared times z prime. That's that part. Let's move the x's across. There's an x squared here, and that's downstairs. So when we move it across, it becomes an x cubed upstairs. And this square root of 1 plus x to the fourth would be divided, but I'm going to write that as a 1 plus x to the fourth to the minus a half. In other words, I'm trying to make it calculus friendly. Calculus friendly in the sense that it's something that we could try to integrate. And now we're like, ooh, we've pretty much separated. In fact, this is one way that people are saying, okay, looks separate to me. I would go one step further just because I do. So x cubed 1 plus x to the fourth to the minus a half dx. And now, fingers crossed, our integrals are going to be something we can actually integrate. Well, we don't have to cross our fingers that hard. I mean, they're not going to give us something we couldn't do, would they? Not intentionally. Not intentionally. So we have 1/3 z cubed. Okay, that's good. I like that. Now, over here, x cubed 1 plus x fourth to the minus a half looks complicated if you think about it like, 1 plus x fourth. That looks like going to be like some crazy trig sub or no. But no. It's simple substitution. So what we would have is here, you'd say, make this your u, then the inside part, right? Substitution, look for things on the inside. Then our du would be 4x cubed dx. Well, we have an x cubed dx. So this would become the integral of, well, I got to somehow get the 4, so I can think of it as 1/4 du. So 1/4 du equals x cubed dx, so 1/4 u to the minus a half times du. Now, we're getting close. You add a half, add 1 to minus half, you get a half. That's u to the half. then you also have to divide by half, and so this would end up becoming 1/2 u to the 1/2, and then of course plus c. Okay, so that's that integral. So that means that 1/3 z cubed is equal to 1/2, and then we have 1 plus x to the 4th to the 1/2, then plus c. All right. Well, we're almost there. What's the next thing to do? Well, next thing to do is let's multiply through by 3. And then remember, z is xy. So, running out of space, I'm going to put this up here. So, we get that 1/3 xy cubed is equal to 1/2 1 plus x to the 4th to the 1/2 plus c, multiplying through by 3, xy cubed equals 3/2 1 plus x to the 4th to the 1/2. 3 times c is still c. So constants absorb constants. I'm really good at that. I forgot to put my parentheses over here. Take the cubed root. X times y is the cubed root of 3/2 1 plus x to the 4th to the 1/2, excuse me, plus c. And then if we divide, we can say our final answer, 1 over x cubed root 3 over 2, 1 plus x to the 4th to the 1/2 plus a constant c. So there's a square root inside of a cubed root, and of course there's this constant which can be arbitrary. Wow, what an answer! What an answer! But we got it. We got it. That's great. That's great. Okay, so that means that we finished that one. All right, let's do it with a quadfecta, as they say. I don't know if anybody uses the term quadfecta, but we're going to finish that last one as well. X plus e to the y prime is equal to x e to the minus y minus 1. Now, what's the substitution to make here? That's actually a great question. It's not so clear what is the, what's the right substitution to be making here. But I would say one thing I'm looking for is a function in a function. Now, y is the thing we're taking derivative of. So I'm looking for that inside something. And I see it's e to the y. So that's like, all right, since I see it's inside e to the y, that's probably where I'm going to focus my energy. So let's think about what we have. X plus e to the y prime equals x. Now, e to the minus y is like x over e to the y. So let's get rid of that fraction. We'll multiply everything through by e to the y. So we get x plus e to the y times e to the y times y prime is equal to x minus e to the y. Okay, well, that's promising. Now, like we said, again, I'll highlight it here. The fact that y is inside e to the y, and in fact it's always showing up as like e to the y, says, hey, let's make e to the y be our substitution. So set z equals e to the y, and then we get that dz, or z prime, I should say, is e to the y prime. We have an e to the y. Perfect. Perfect. It's almost like they planned for this. Well, because they did. They did plan for this. So that's amazing. That's amazing. All right. So we get x plus z times z prime is equal to x minus z. Now, I'm going to move this up because I think we all know where we're going here. What's going on here? How do we solve this one? Well, if you look at it, what do we have? You'll see we have everything's a polynomial term, all degree 1. It's homogeneous. So this could be rewritten as 1 plus z over x, z prime equals 1 minus z over x. So I'm saying, aha, this is homogeneous. Let's multiply everything through by 1 over x. And now we're going to do another substitution. And you're like, what? We already did a substitution. Are we allowed to do a second substitution? This is madness. No, this is math. That's how we do math. We do it as many substitutions as we need. And sometimes we have to do a sequence of them. Well, oftentimes, of course, that's just a reflection of, we almost had the right idea, but we weren't quite there. But that's okay. Refine, refine, refine. Now, the only challenge is we've got to think of a new letter because we've already used x, y, and z. And, of course, for mathematicians, the letter after x, y, and z is w. I know, it's weird, but that's what they do. Mathematicians, gotta love them and their lack of knowledge about the alphabet. So we're going to substitute w equals z over x, or we could say, look, z equals w times x. So we get that z prime is equal to the root of the first times the second plus the first times the root of the second. And so that's times 1. Okay, so updating. We now have 1 plus w times w prime x plus w is equal to 1 minus w. All right. Well, as they say, Well, okay, let's keep going because, well, we should keep going. All right. Divided by 1 plus w, we'll have w prime x plus w is 1 minus w over 1 plus w. Subtract w prime x equals 1 minus w over 1 plus w. Subtract w, well, which is 1 plus w over 1 plus w, which would become 1 minus w minus w, minus w, minus w squared, all over 1 plus w, which is 1 minus 2w minus w squared over 1 plus w. Now, over here, this other side, the x, dw, dx. All right. Now, I know you're nervous. I know I'm nervous. Let's be nervous together. And let's just be like, come on, we can do it. Come on, differential equation. We believe in you. It's going to be separable. So we would have 1 plus w over 1 minus 2w minus w squared dw is equal to 1 over x dx. Now, the next step, we've separated. Now we integrate. One of these is going to be easy to integrate. One of them is maybe going to be easy. The 1 over x is the one we're like, ha, I know that. So, this is going to be log x plus c. Any hope here? Well, this doesn't factor nicely. I mean, it will factor, but it won't factor nicely. But notice something. We can make a substitution. You're like, what? Again, Steve? I know. If you say u equal that, what would du be? Then du would be minus 2, and and then minus 2w times dw. Or you can say, oh, minus a half du is equal to, if we divide through, 1 plus w dw, which means that the integral becomes, on the left-hand side, minus 1/2 1 over u du. So that's minus a half times log of u. We already have the plus c over there. Or that's minus a half times log of 1 minus 2w minus w squared. Okay, so there we go. Now let's go ahead and just to make things a little bit nicer, because you know what, we deserve things to be a little bit nicer, let's multiply through by minus 2. And let's see what we get. So multiplying through by minus 2, we will have log 1 minus 2w minus w squared equals minus 2 log of x plus c. Well, this of course is the same as log of 1 over x squared, because the minus 2 can come in as a power. And now we're like, all right, good. Take both sides, put it into the exponential function, and we get 1 minus 2w minus w squared is equal to, and here, e to that constant will become a constant multiplied by e to the log of 1 over x squared, which is 1 over x squared, so some constant over x squared. Now we work our way back through two substitutions. So remember, w is z over x. So 1 minus 2 z over x minus z over x squared is equal to constant over x squared. Let's multiply through by x squared, just so things look nice. Get rid of all our fractions that way. We'll get x squared minus, excuse me, minus 2zx minus z squared equals a constant. All right, now we're in our home stretch. What's z? Z is e to the y. So we plug that in, and so we're going to get x squared minus 2z. Whoops, not z. Z is e to the y. 2e to the y times x minus e to the y squared is e to the 2y equals some constant times c. Whew, my goodness. Wow. Yes, we could solve it. Isn't that beautiful? You know, and in theory, one could even go and use the quadratic to actually find an explicit function for y. But you know what? We love ourselves enough to say, this is a great way to put the answer. Good on us. Good on us. So, all right. Wow. Wow. Amazing. That's amazing. That's beautiful. Oh, wow. Good job. Good job. Okay. All right. Well, and anyways, that was the last one. So 4 for 4. We succeeded. You know, many possibilities. And, well, of course, along the ways, a lot of practice. And as always, more practice is good for us. We joined this problem already in progress. Now, the goal here is to say, hey, you know, if you have some higher order derivatives involved, instead of thinking of it as a second order differential equation, you can think of it as a sequence of two first order differential equations. Now, you can't always do this. And the way it works is there are some special cases. And so they're both highlighted here. So the first special case is when there's no y. It's like, hey, I'm skipping over y, and so the lowest derivative that shows up is y prime. And you say, oh, well, that's a simple idea. Set z of x to be y prime, and then z prime is y double prime, and this first equation becomes x squared z prime plus 3xz equals 2. All right, let's follow that one through. So what happens? Well, this is a linear first order because there's no second derivative anymore. Divide by x squared. So z prime plus 3 over x times z is equal to 2x, whoops, not 2x, 2 over x squared. And we come here, we integrate 3 over x, and that's not so hard. You know, after you do a couple hundred of these, it becomes second nature. You know, even before then, it becomes second nature. So our integrating factor is rho of x is e to the log of x cubed, which is, whoops, x cubed. So you come back to your original differential equation, the one with the leading term 1 times z prime, multiply both sides by x cubed, and we see, lo and behold, we get x cubed times z prime plus 3x squared times z equals 2x. Well, by design, the left-hand side is going to be good. It's the derivative of x cubed times z. And the right-hand side, that actually looks pretty appealing to us because we are anticipating that we're going to have to integrate. And among things to integrate, it's one of our more favorite ones to integrate. Because we see we get x cubed times z is equal to the integral of 2x will be x squared plus z. And so divide through by x cubed. That tells us that z is equal to x squared over x cubed is 1 over x, and then plus c over x cubed, which mysteriously I'll write as c x to the minus 3. But we're not done. We always got to substitute back. Our substitution was z equals y prime. So this is y prime. So great, we have y prime. So we have to integrate. So we say, all right, integrate. We get y equals, well, integral of 1 over x log x. The integral of some constant c x negative 3, well, you'd add 1 to the exponent, I'd make it negative 2, and you divide by negative 2. But wait, there's a constant there. So that constant can absorb the divide by negative 2. So you end up with plus a constant over x squared. And a new constant. Because, of course, every time we do an integral, we get a constant. And it's a second order, so we should expect 2 constants. And we're done. So that's it. So x squared y double prime plus 3xy prime equals 2. Boom. Beautiful. Beautiful. Just right. Fantastic. All right. Now, that's one thing that could happen. Another thing that could happen is that when we have our differential equation, there's no x's involved. So it's, in other words, it's all y's and y primes and y double primes. Now this one is a little bit more counterintuitive if you look at what happens here. So grab our piece of paper. Now what happens is we say, look, do your substitution almost like before, z equals y prime, but now, here's the twist. It's not z as a function of x, it's z as a function of y. So the twist is when you take derivatives, y double prime is z prime times z. Now where this z is coming from is the chain rule, because we get rid of the outside, which is z prime, leave the inside alone, times get rid of the inside, which is y prime, which is z. So that's why there's a twist. So we get ZZ prime equals Y double prime. So we're just, we get Y ZZ prime equals 3Z squared. Actually, you know what? I think there's enough space. We'll just use this piece of paper here. Okay, finishing up. What do we see? Well, this will become, we can separate. So this is saying that dz over z is equal to 3 dy over y. Move stuff around. We integrate both sides. And we get that natural log of z is equal to 3 natural log of y plus some constant c. Well, this is the same as natural log of y cubed plus c. Put both sides into the exponential function, and so we get the z by itself. So we get that z is equal to, well, e to the log of y cubed is y cubed, and e to the c, e to a constant, is a constant. But, so we'll just replace it by c. This plus becomes multiplication. And now this z is y prime. Well, the same as before. So I just write y prime. So we get y prime is some constant y cubed. Now we integrate. Integral of y prime is y. Integral of y cubed. Wait, we can't just integrate. That's not an x, that's a y. We got to separate yet again. So we would have dy over y cubed is equal to some constant dx. And now integrate both sides. Okay, now this is like y to the minus 3. And so when we integrate, well, it becomes y to the minus 2, then you divide by minus 1/2. So we would have, go this way, minus 1/2 y to the minus 2. Oops, there's a minus 1/2 there. There we go. Is equal to some constant x plus some other constant d. Now, multiply through by minus 1/2. And what can we do? Well, we'll get y to the minus 2 is equal to cx plus d. Okay. Now I know you're like, why do you keep doing that? Well, because I like my answers to look nice. And constants can absorb constants. So that when I multiply the negative 2 times that constant, it's just like, okay, update it to a new constant. So really, this is like, these aren't the exact same value for c. It's just, this is a symbol saying it's some constant. And if I multiply some constant by a number, it's still some constant. Now, if you want to solve for y, and why not, we're right there, we say, great. Y would be, raise both sides to the minus 1/2. Cx plus d to the minus 1/2. Done. Wow. What a fun problem. What a great problem. So let's do one final problem to wrap up. Consider the initial value differential equation 2xy y prime plus y squared minus 3x squared equals 0, where y of 2 equals 3. And we're going to find a solution either in implicit or explicit form by doing each of the following. So we're going to solve this differential equation in 3 different ways. Now you might say, woo, 3. Don't we have like 3 ways to solve? We've got separable, we've got first order, and we've got exact. Yes. We can actually use all 3 of those different techniques. This sort of problem emphasizes the idea there's not one way to solve a differential equation. Sometimes by making a different choice at the start, we lead to the same outcome, but a different journey. So it's sort of like one of those choose your own adventure books. I don't know if they still make them, but when I was a kid, there was like, you'd read a book and it says, okay, if you want to do this, go to page 7. Want to do that? Go to page 24, and then you could navigate. Well, that's us. We're going to choose our own adventure and find our solution. So not only are we going to be confident, we're going to be like super confident about how to solve this particular differential equation. All right, so we have our differential equation. We're going to start part A, using that this is an exact equation. All right, now exact is one of our favorites. And this one, maybe it doesn't jump out to us right away. It's like, aha, go for exactness. But, well, it turns out it is. So let's try this. So I'm going to grab a fresh piece of paper here. So this is part A, and this is exact. So just keeping track. So if it were to be exact, so this y prime is dy dx, then that could be rewritten as 2xy dy, and then this other part, y squared minus 3x squared times dx equals 0. Well, let's find out. Okay, so we're going to integrate 2xy dy. So y is our variable, x is a constant, so the x stays as x. The integral of 2y is y squared, and then there's, of course, some constant function of x. The other integral, y squared minus 3x squared dx, well, now we're integrating with respect to x. Y squared is a constant, so y squared is a constant, so the integral of that would be x times it, so xy squared, and minus the integral of 3x squared, that's a popular one, that's x cubed, plus, okay, something which depends on y. And we do our quick check to say, well, they said it's exact, but can we always trust them? And we say, aha, these match, which is good. That means it is, in fact, exact. So we get that our solution would look like the following. I'm going to move this up so we have space. So we're going to get x, y squared, the matching part. There's no part only involving y, and then there's a minus x cubed equals some constant e. Now, are we done? No, because I covered up the problem. If I uncover it, you'll see y of 2 equals 3. So that really tells us we're going through the point 2, 3. So when x equals 2, y equals 3. So to finish, we have to solve for e. So we would say, okay, 2 times 3 squared minus 2 cubed equals e. Well, let's see, that's 18. Subtract 8, which would be 10. And therefore, our final answer is xy squared minus x cubed equals 10. And that would be a great answer. Now, because we're going to anticipate that we're going to do this again, we could say, hey, we could also write this as y squared is equal to 10 plus x cubed over x. And so y is the positive square root of 10 plus x cubed over x. Now you might say, how are you so sure it's the positive square root, Steve? Well, because when we plug in a 2, we got a positive 3. So this is another way we could write our answer. So in the future, for parts B and C, we better get this same answer. That or mistakes were made. I hope not. I hope not. Let's be confident. No mistakes. That's our goal. That's always our goal. Well, let's try part B. Seeing that this is homogeneous. Oh yeah, see how there's a xy, a y squared, and an x squared? Everything is like a degree 2. And so we're gonna do it by homogeneous. Okay, so for part B. So homogeneous. All right, let's follow our process here. So starting with our equation, what we do is we're going to multiply by something so that everything looks like a y over x. Now, since everything's of degree 2, you'd multiply by 1 over x to the 2. So this becomes 2 y over x, y prime, plus y over x squared minus 3 equals 0. All right. And, oh yeah, let's recall y of 2 equals 3. We'll make a note there so we don't have to look back again. So what happens here? Well, we know our substitution. That's our y over x. That's our substitution that we're making. So z equals y over x. Now we're not done because we also have to account for that y prime. So that says y is equal to x times z. So y prime, well, take the first times the root of the second plus the root of the first times the second. Okay, so that's our substitution. We carry out our substitution, and what do we get? Well, we're going to get 2z times, here, xz prime plus z, plus z squared, and minus 3. All that equals 0. All right, well, interesting. Well, let's see what's going to happen. So we'll have 2xz, z prime, and then plus 2z squared plus z squared. So that's plus 3z squared, and then minus 3 equals 0. Well, let's move the part not attached to the z prime across. 2xz dz dx is equal to 3. In fact, since they both have 3, let's go ahead and factor that. 3 times 1 minus z squared. And now, well, we'll rewrite a little bit. Okay, so what will this become? We have that this will become, we're separating, right? Because when we take something and use homogeneous, it turns into separable. 100% of the time it's separable. Now, it also might be like 25% of the time it's something else. And you're probably thinking like, Steve, those percentages don't add up. Well, yeah, because something can be more than one thing. It's a beautiful thing. All right, so we're going to have 2z divided by 1 minus z squared. So I'm leaving the 2z there. dz is going to be equal to, over here, 3 over x dx. And now, integrate both sides. Well, very lucky for us, we don't have to work hard, because if you think about the denominator, set this to be u, it's almost, the derivative is almost the top. Almost. Except for a minus. Well, that's easy to fix. So, minus log 1 minus z squared. On the other side, 3 log x plus c. Well, let's move the minus across. So plus, make that a minus. And of course, the c, as always, absorbs constants. Raise both sides, e to that power. And what will we get? Well, we're going to get that 1 minus z squared is equal to, now here, this part is the same as log of x to the minus 3 is 1 over x cubed. So that would be 1 over x cubed. And then you get that e to the c is just some constant c. All right. Well, we're getting close here. Now, from here, what I would do, because I'm the one doing it, so this is what I would do. It's always what I would do. I'm going to get z squared by itself. So I'm going to write this as z squared. And I'm just going to swap sides here. So equals 1 plus c over c times 1 over x cubed. I know, you're like, Steve, But we're okay, remember, because, yeah, this would normally come across as a minus c over x cubed, but it's like, oh, see, or if you like that's just absorbing that. And, okay, great. Wow. Okay, but z squared, that's going to be y squared over x squared. So, multiplying across, we get y squared is equal to, here we'll get x squared plus some constant over x. And now we can actually solve for our constant because we can plug it in. So when we plug in x equals 2, we should get y equals 3. So we have that 9 is equal to 4 plus some constant over 2. 2 squared, 2. So subtract 4, multiply by 2. This says, c equals 10. So we get that y squared is equal to x squared plus 10 over x, or finally, taking the square root, y is equal to the square root of x squared plus 10 over x. Good, good. And if we pull up the previous one, we'll see they're actually the same. Now they have a slightly different way of writing it, but see, if I put it over x, you get x cubed plus 10 over x. That's what we have, 10 plus x cubed over x. So we got the same answer. What? No surprises. Of course we're going to get the same answer. But one part left. That's right. The fun continues. Part C, our last part. Okay, now, this says making the substitution v equals y squared and then doing a linear first order. Okay, now actually, whenever you do a substitution, y to a power, that's Bernoulli. So, cool. So it turns out we can also do Bernoulli. Like, wow, all these things all wrapped in one. Okay, so let's recopy it. 2x y prime plus y squared minus 3x squared equals 0. Y of 2 equals 3. And so for part C, this is Bernoulli. I know, it doesn't say Bernoulli, but again, anytime it's y to a power, that's Bernoulli. That's what Bernoulli is, y to a power. Okay, so we're doing a Bernoulli, and I've been using x's instead of v's. Well, you know, we can still use. I've been using z's instead of v's. We'll still continue to use z. Why not? Force of habit. Okay, z equals y squared. We'll move this up. We know what the answer is. We just have to enjoy the journey to get there. So we get z prime equals 2y y prime. And wow, that's very convenient for us. So we get x z prime plus z. And this minus 3x squared, move it back to the other side. Okay, got to make the z prime have a 1 in front. So z prime plus 1 over x. Actually, do we? Well, okay, all right. We'll go through the process. We can, if you look for things, you'll be like, hey, that's the derivative of x times z. Yeah, it is. We'll get there. But if you spot that right away, go ahead and use it. And if you don't spot it right away, go ahead and do the process. It's okay. There's no points for like, hey, you were clever. We're going to get bonus points. No. You're just get there a little sooner. No problem. Okay, so there is our integrating factor is x. And so, x z prime plus z equals 3x squared. But this side is indeed the derivative, whoops, off the page, the derivative of x times z. All right. And now we, of course, integrate both sides and see what we get. Well, right-hand side is pretty straightforward. Left-hand side, pretty straightforward. X times z is equal to x cubed plus c. But we know what z is. Z is y squared. So we have x y squared equals x cubed plus c. Well, let's plug in and solve for c. We're here. Let's do it. So we have 2 times 3 cubed is equal to 2 cubed plus c. 2 times 3 squared. So that's 2 times 9, which is 18, equals 8 plus c. That says c equals 10. So we have x y squared is equal to x cubed plus 10. Well, okay. Divide by x. We get that y squared equals x squared plus 10 over x. Or y equals, again, the positive square root. And we know it's the positive square root because we want to get a positive number out. Square root of x squared plus 10 over x. Same as the other two parts. Wow. Look out, crowd's growing crazy. All right, well, okay. That was kind of, it's fun to see that you can do things in multiple ways, so be adaptable. Don't try to think like, oh, let me find the best way. Find a way that works for you, and it's okay to take a few seconds to say, is there another way I could try? And you know what? If you don't see all the ways to solve a problem, it's okay. You only need one. One's enough. All right, well, I think that's good for now. See you later.